Hey everyone, and welcome to CS Course Companion. Today, we are diving right into the absolute bedrock of computer science, data structures and algorithms. Seriously, this is the secret sauce that powers pretty much all the tech you use every single day.
So, to kick things off, let me ask you a question. You've got Google, the biggest search engine on the planet. You've got Amazon, a global e-commerce giant. And then you have that simple contacts app on your phone. They seem worlds apart, right? But believe it or not, they all share one fundamental, massive challenge.
And that challenge is this. They all have to conquer digital chaos. Every single one of them has to manage, search, and sort through unbelievable amounts of information at lightning speed. And the tools they use to do that? Well, that's exactly what we're going to break down today.
So here's our game plan. First, we'll look at the blueprints for organizing all that data. Then, we're going to hold a great sorting race to see which methods are fastest. After that, we'll see how to find a needle in a digital haystack, compare two very different ways of solving problems, and finally, we'll learn how computer scientists actually measure an algorithm speed. Let's get into it. All right, first up, organizing digital chaos. I want you to think of data structures as the shelves, the boxes, and the filing cabinets of the digital world. You just can't build an efficient system if you don't have a smart way to organize all the stuff inside it.
Now check this out. Data structures basically fall into two main camps. On one side, you've got linear structures, like an array. This is perfect for something simple, like a to-do list where one item just follows the next. But on the other side, you've got nonlinear structures, like a graph. This could represent a social network, right? With all those complex connections between friends. Choosing the right structure is the very first critical decision a programmer has to make.
Okay, so once your data is stored, you usually need to put it in some kind of order. And this brings us to our next section, the great sorting race. Now, an algorithm is just a set of instructions, but as you're about to see, not all instructions are created equal, not by a long shot.
First up in the race is Insertion Sort. This one is super intuitive. You'll get it right away. It just goes through the list, picks up an element, and slides it back into the right spot in the part of the list that's already sorted. It's exactly how you'd sort a hand of playing cards. It's simple, it's effective, but maybe not the fastest contender.
Now, for a totally different strategy, we have merge sort. This is a classic divide and conquer algorithm. It takes a big, messy list and just keeps breaking it down into smaller and smaller pieces until you have a bunch of tiny one-item lists. I mean, a one-item list is already sorted, right? And from there, it carefully merges them all back together in the correct order. It's a really powerful idea.
And then there's bubble sort. This one repeatedly steps through the list, compares two items that are next to each other, and swaps them if they're in the wrong order. The biggest items kind of bubble up to the end of the list. It's often one of the first sorting methods people learn, but its performance, well, let's just take a look at the results. Okay, here are the official race results. We measure this using something called Big O notation, which is just a fancy way to describe how an algorithm's runtime grows as the list gets bigger. Now, look at merge sort. It's super consistent, with a worst case of O(n) log n. Now, look at insertion and bubble sort. Their worst case is O(n) squared. That might not sound that different, but believe me, it is dramatically slower as the list grows. The takeaway here is huge. The algorithm you choose matters a lot. So, why do we care so much about sorting? What's the big deal? Well, once your data is in order, you unlock some truly incredible superpowers for finding things. And that brings us to our next topic, finding the needle.
You really have two main ways to do this. There's sequential search, which is the brute force method. You start at the beginning and check every single item. It works, sure, but it can be really slow. And then there's binary search. It requires a sorted list, but the payoff is insane. You jump to the middle of the list. If that's not your item, you instantly know whether to look in the first half or the second half. Boom, you just eliminated half the list in one go. You just keep doing that, having your search area every single time.
And this right here is why it matters. Just look at these numbers. To find one item in a list of over 4 billion items, a sequential search might have to check all 4 billion of them. Binary search, it takes a maximum of 33 comparisons. 33! That is an absolutely mind-blowing difference in efficiency. It's just incredible.
Okay, now let's switch gears a bit and explore two different ways you can actually write the code for these things. We're talking loop versus leap, or more formally, iterative versus recursive thinking. It's all about how you handle repetition.
The perfect example for this is the Fibonacci sequence. The iterative solution is straightforward. It uses a simple loop, building the sequence one step at a time. Its performance is linear, or O of n. The recursive solution, on the other hand, is really elegant. It defines a Fibonacci number by just calling itself with smaller numbers. But this elegance comes at a terrifying cost. It has exponential time complexity because it ends up recalculating the same values over and over and over again.
And I mean it when I say the cost is terrifying. I am not exaggerating. To calculate the 100th Fibonacci number, the iterative loop takes about 101 nanoseconds. The recursive approach, it would take an estimated 13 days. And it gets so much worse. To calculate the 200th, you're talking about trillions of years. This is probably the single most important lesson about algorithms. A tiny choice in your design can lead to an astronomical, galaxy-sized difference in performance.
So, all this talk about performance brings us to the formal language we use to discuss it. How do we actually measure an algorithm's speed and predict these huge differences? Well, it all comes down to the power of big O. You see, time complexity isn't about measuring seconds or minutes on a stopwatch. It's about counting the number of basic operations an algorithm performs relative to the size of the input, which we just call n. It tells us how the runtime will grow as n gets bigger. Will it grow in a straight line, or will it explode upwards? That's what we need to know.
The whole point of big O is to focus on what matters most when n gets really, really big. Just look at the columns on the right. When n is small, like 10, the other terms in the equation matter a little bit. But when n is 1,000, that n squared term becomes almost the entire value. It just completely dominates everything else. So we drop the less important terms, and we say the algorithm's complexity is O of n squared.
So, what are the big takeaways from all this? Let's recap. 1. Data structures are the foundation you build everything on. 2. Your choice of algorithm, like merge sort over bubble sort, has a massive impact on performance. 3. Sorting your data first can unlock hyper-fast searching. And 4. Be careful with elegant-looking solutions, like recursion, that can hide some seriously dangerous performance traps.
And that's our whirlwind tour of the fundamentals of data structures and algorithms. We've really only scratched the surface, of course. So where should we go next? Should we dive into something like dynamic programming, or maybe explore graph theory? Let me know in the comments below what you want to learn about next.
If you found this useful, whether you're studying for a class or you're just curious, make sure to hit that subscribe button for CS Course Companion. We're going to be breaking down core CS concepts just like this every week. Thanks so much for watching.